Hello. Welcome to Tokenization, the building blocks of LLMs. So tokens are the units of observation, right? They're the fundamental units of observation that large language models use, much like atoms are the fundamental units of matter. They're converted from text to integers so transformers can process it. Most papers involving LLMs will mention the context window size used. So for example, you've got this paper, language models are unsupervised multitask learners. And you're going to see in the beginning that the vocabulary, something like this vocabulary is expanded to 50,257. We also increased the context size from 512 to 1,024 tokens, and a larger batch size of 512 is used. So you're going to see the number of tokens that they have. And the transformer could only attend to at most n previous tokens when predicting the next token. So here's a couple of examples. GP2 has about 1024, GPT-3 has about 2048, Llama 2 has about 4096. Training on more tokens generally improves model performance. First, I'd like to make an important point regarding what I just spoke about, right? With respect to the size. A model that produces or consumes more tokens for the same task doesn't automatically perform better. So when you see those token sizes, it's not necessarily something that will lead to better performance. There's multiple things that you have to take into account. What matters more is how efficiently those tokens represent information, right? The tokenizer quality and how the model uses them internally, the architecture and the context handling. So more does not equal better. So I'm going to give some examples of tokens. Different tokenizers will have different number of tokens, right? Depending on design, vocabulary, and subword algorithm, all right? So I do want to make that point. So we can see tokens on the word level. We have an input, I love machine learning. We're going to get 4 tokens. On the subword level, we're going to get 5 tokens. So notice that the subword level, we get more tokens, right? We get learn and ing is the extra. And then finally, on the character level, we basically get 23, okay? You're going to see that later on, like the UTF byte encoding, we're going to have to use it on the character level. But examples on the word level are going to be given just to simplify and also illustrate some of the major points of the algorithm, right? So that's what I'll be doing shortly. So first, let's talk about what's the problem with the word level tokenization, because obviously that would be the most, I guess, desirable from our perspective, right? I mean, I wouldn't want to mess with stems or character level, seem pretty messy, right? But there's some problems with just looking at words solely as words. And we could use the example of unhappiness and like something like reinventing, right? We could see that these two words have prefixes and prefixes and suffixes, right? For unhappiness and reinventing, right? Unhappiness, and then reinvent being the root word, and then ing. Okay, so from this from these words, we could imply multiple things. But simultaneously, they're rare words, right? We might not get it in this form. We might get unhappy. We might get reinvent. So if the rare word, if your training corpus never saw unhappiness, the model can't predict the word, okay? And the model treats it as a single atomic token, losing internal meaning. the LLM model wouldn't be able to tell the word unhappiness is built from meaningful parts, right? So I just clarified that point, but let's be a little bit more specific with the word unhappiness. So on, it doesn't know that on negates happy. It doesn't know that happy is an emotion. And then this, it doesn't know the noun suffix. Therefore, it treats the word as an entirely new, unknown symbol, and it can't generalize. So you could see the usefulness of looking at it on a subword level. Now let's talk about morphology. This is something that that produces something called a morpheme, which is the smallest unit of meaning in a language. So when we look at words like bread, man, that would be a single morpheme. And we saw that the word unhappiness, though, carries multiple morphemes, right? We have un, which is not, happy, which is joy, this, which is a state or quality, right? So there are three morphemes for the word unhappiness. Okay. So it could be advantageous to look at things from a morpheme level. It would be advantageous to look at things from a morpheme level because it implies more meaning. It's a richer vocabulary. So then there's also tokenization by subword. So the US has something like I love machine learning, right? English. And then we've got the text here. And then it could be broken down into token IDs. Okay. There's South Korea. The input is, I'm just saying it basically in Korean. I love machine learning. It's 나는 machine learning을 사랑한다. So that means like I love machine learning as well in Korean. You can see that particular this particular sentence has a little bit more than the English. I mean, just by looking at the color coding. And we've got more token IDs to represent, token integer IDs to represent that particular sentence, okay? And we got French as well. The input is j'aime machine learning. J'aime le machine learning. It's been a while. I took French in college, so pardon me. But we've got here 5 tokens. Okay, so English seems to be the most compact for this particular word, but obviously it's the way that the tokenizer basically produce the words, right? I mean, we could have tokenizers that break up machine learning into learn and ing. Okay, so it's really depending on the type of tokenizer that you're using. I think for this, I use GP2 in the Vercel tokenizer app, which I'll give you the address to in a little bit. A token can include a space as well. In the Korean example, we do have a carriage n at the end, okay, space at the end. And tokens are mapped, like you saw earlier, to unique integers, which serve as indices into the model's embedding table. So the neural network or transformer can process text as numerical vectors. Okay, so this is where the token IDs are used, and that's what's going to produce those embedding vectors later on in the pipeline. And we'll see embedding vectors, word vectors in a later video. But for now, we're going to be focusing on what the fundamental unit of a tokenization process looks like. So I said this earlier, the number of tokens depends on the model. We've got GPT 3.5 Turbo that's got 3 tokens for 1776. Google Gemma 77B, it's got 5. And then GP2, which has 2. I'm going to give an example now also for tokenization for code. Um, it's a big thing now because people are using it to vibe code and asking LLMs to solve problems or whatnot. So it's important to kind of know like how many tokens um, different language models produce. So here's an example of some code. Numbers is equal to 1 to 5, and then we've got a for loop if it's even, and then print if it's odd, right? We go through each of the numbers and see if it's even or odd. You can see in the GP2, there's a 71 total token count versus C1 100K base 51. There's a 51 token count, right? So the white spaces have basically been eliminated, right? You could see on the left for the second line after the for loop that there's about 3 color codings to that versus 1 in the second code. And if you'd like to experiment with this, just trying to see like how many tokens these tokenizers produce, you could check it out at this particular website. I'll have this link in the description. So we saw that the compactness of the second set of code in the earlier one, and we saw that there were less white spaces, right? So why does compactness matter? So the bucket has 4,096 tokens. GPT-2, I love machine learning, has 9 tokens, right? So 9 tokens per sentences, then there's about 455 sentences. In the CL100K base, we saw the same sentence with 6 tokens, okay? And the 6 tokens per sentence, you have 682 sentences, okay? So you've got a larger context window. So that's one of the reasons why compactness matters. You're not wasting space, right? We don't want 3, 4 token IDs for white spaces instead of having just 1. So earlier I talked about we gave an example with different languages, Korean, French, English, and they've got different tokens. But I'd like to go a little bit more in depth because LLMs are trained on, I believe, a lot of I don't know the exact language, but I mean, I'm sure every language on earth, right? Besides some of the more esoteric ones that say like Eskimos would use or native Indians would use. So let's go into the types of languages. First, there's an analytic, isolating. Words are mostly single morphemes. Grammatical relationships are expressed using separate words or word order. There's something called synthetic. Words contain multiple morphemes, and we saw that in Korean, right? But it's not restricted to Korean, it could be English as well, often encoding grammatical features internally. And out of the synthetic, we've got one is fusional. One morpheme encodes multiple grammatical categories, tense, person, number, gender. We saw that with the French example. And then 2 agglutinative. Morphemes glued together, each representing one grammatical category. And then polysynthetic, extreme synthesis. One word encodes what would be an entire sentence. Now, polysynthetic is a bit of a strange one. Those are the types of languages that Eskimos and native Indians would use. So let's go through the different language types by country. So the analytic isolating would be English and Chinese. Agglutinative synthetic would be languages like it's Korean, Japanese, and language from Turkey. And fusional synthetic would be French and Russian. Polysynthetic, like I mentioned earlier before, it's Eskimos and Mohawk Indians. So analytic languages, I love machine learning. There's 5 morphemes. We've got the pronoun, the verb, the noun stem for machine, the verb stem for learn, and then inflectional suffix for ing. Okay. We've got fusional now with French. Jamais l'apprentissage automatique. There's 8 morphemes for that. Okay. So we've got j'ai, pronoun, mais, which is a verb, le, definite article, apprendre, learn, is, verbal derivation, sage, noun forming suffix, and automatique, adjective stem. Okay, so there's 8 morphemes for that. It's quite a jump. That verb, there's 2 morphemes, right? Lexical meaning and present tense, plus first person plus singular. Okay. Now I'm going to get into agglutinative for Korean. So it says 나는 machine learning을 사랑해. So it's like I love machine learning, and that could be broken down into 6 morphemes here, right? 나는 machine learning을 사랑해, right? So I, which is 나, 는, which is a topic particle, machine learning, which is the object, 을, object particle, 사랑, love, 해 is present tense informal. So you can see the grammatical structures from English to French to Korean are pretty different, right? So that's going to create more morphemes, okay? And hence a larger vocabulary, okay? You could also in Korean say what I just said is 저는 machine learning을 사랑합니다. So this in red, 사랑합니다. I know that you guys don't speak Korean, but you could kind of see the intonation of what I'm saying. That is a polite present tense formal, right? That 합니다 replaces 해, okay? What I'm trying to get at from this example is basically the language is completely different. So in Korean, you could speak to people like you're speaking to your friends, but the language expands based on who you're talking to. So you could be talking to an adult and you have to use a different convention. Okay, there's a different speaking convention, which consequentially leads to more words, okay, and a larger vocabulary, okay? So that could affect the LLM, is what I'm trying to get at. So agglutinative languages like Korean tend to have more morphemes because they explicitly encode grammatical and social information. But modern tokenizers are optimized for English, so they often split these morphemes inefficiently into many tokens, okay? So that's something to be mindful of, okay? When you're working with LLMs, especially the fact that there's just so many languages, so many different grammatical structures. So that's what I was trying to get at with the 3 examples previously. So here's polysynthetic example, and this is something that I'm probably not going to even be able to pronounce, right? But I will have to go to the airport. In the Inuit language is this long string here, okay? And you've got each number corresponding to a particular character. The way the tokenizer divided this, like I wouldn't be able to even have any understanding of the convention of how it was split. But we could see that it's kind of just one long string, okay? And then there's corresponding token IDs. And it comes out to about 15 tokens, okay? So quite a lot compared to the rest of them. Now I'm going to get into Unicode. Um, so starting in the 1960s, the Latin characters used to write English, like the ones used in ASC2 in this sentence, were represented with a code called ASC2, American Standard Code for Information Interchange. ASC2 represents each character with a single byte. A byte can represent 256 different characters, but ASC2 only uses 127 of them. The higher order bit of ASC2 bytes is always set to 0. And we could see the character for each character, right? There's a code point and the UTF-8 byte. A code point is a unique number assigned by Unicode to represent a single character. Unicode gives you numbers, code points. UTF tells you how to turn those numbers into bytes. So you see that X68, X65, X6C, X6F. Unicode defines a large numeric space, U plus 00 to U plus 10 FFFF, and each number in that space is a possible code point. That space allows for 1,114,112 possible code points. Only about 150,000 are currently assigned to actual characters. So what's the big deal with UTF-8? The reason why UTF-8 is important is because basically the entire internet is represented in UTF-8 bytes. Okay, so when data is crawled, it's basically UTF-8 that we're looking for, not words, not morphemes. So this is how it's usually represented. So here's some code. I'm going to go hello. Let's encode that in UTF-8. We do a for loop, right? The byte in B, and we print it, and we get that 0, x68, x65, x6c, x6c, and x6f. Okay, so this is represented in bytes. Python is pretty friendly. You'll see B hello, right? So it's prettified by Python. You're not going to see it represented in that byte format. I do give a notebook link in the description, so you could check that out, right? You could play with like how these characters are transferred into bytes. So we saw previously that we had Korean, we had French, Russian, and whatnot. So they're not all going to be represented by characters in ASC2. So Chinese has about 100,000 Chinese characters in Unicode, including overlapping and non-overlapping variants using Chinese, Japanese, Korean, and Vietnamese, collectively referred to as CJKB. Whenever we need to represent character and text string, we write an encoding of the character. There are numerous amount of encoding methods, but UTF-8 is the most ubiquitous. And as I said earlier, the entire web is encoded in UTF-8. On encode UTF-8, I give an example, that's 3 bytes. So that one character in Korean is basically 3 bytes, okay? For those who know Korean, Hangul, the alphabet, that's 3 characters. List, map, int, tent1, we transform that into integers, which there should be 3. Okay. So that's an internal look at what token IDs are like, okay? Let's go into an example of a subword tokenization algorithm called byte pair encoding. So a naive approach is to tokenize text into characters or bytes, which works for every language, produces very long sequences, and weights context on predictable patterns. Tokenizing into whole words is more efficient, but it fails on new words, misspellings, names, emojis, and multilingual text, forcing the use of an unknown token. So we saw that word unhappiness, right? And that would be something that would be difficult if it wasn't in the vocabulary, right? But if we broke it down to on and happy and this, obviously we could do better make better predictions. So in order to resolve this, we've got something called byte pair encoding, and it resolves this trade-off by starting from the small units, bytes, which I mentioned, and automatically learning larger tokens by repeatedly merging the most frequent adjacent sequences in the data. And as a result, common words become single tokens, rare or novel words are still represented as smaller pieces, and the tokenizer remains both efficient and robust across languages. So that word unhappiness, for example, if we just had unhappy and this, we could create a new token, mint a new token called unhappiness, okay? And we still have the smaller pieces as well, right? Unhappy and this, so that we could make predictions with other words, right? So let's give an example of byte pair encoding. He felt unhappy. Being unhappy is common. So you see the two separate words, unhappy. Okay, it's un and happy. That's two different words. We tokenize it. We could see that we've got approximately 11 characters, right? And the sentence could be represented by the following tokens: 10, 11, 6, 7, 12, 13, 6, 7, 14, 15, and 12. And we see that repeating 6, 7 twice, okay? And this would be 11 tokens as well, okay? So we're going to do some accounting and keep track of how many tokens we lose, which is kind of the main point of this, in the sense that we want a more compact representation. Second, we see that 6, 7 seems to be a common reoccurring pair, which I just mentioned, okay? We now mint 6, 7 into 9, 9. So 99 combines 6 on and 7 happy into 99 unhappy. That's a local compression of the sequence, not a deletion from the vocabulary. So that's important to point out. And then fifth, we merge the 6, 7 into 9, 9 and replace it. Okay, so we did the combination. Now we replace it. Now we've got 9 tokens. He felt unhappy. Being unhappy is common. Okay, so we've got 9 tokens now. And I've got I do put an example in the code that I've placed in the description. So thank you very much, and hope you have a great day.